So hi everyone, welcome to this session. We shall be doing further examples on transformer efficiency at various loads. So we shall take this example so that we are able to understand the concepts of efficiency at various load levels. So the example reads, a 120 kVA, 6000 primary voltage, 400 secondary voltage. It is a star-star connected three-phase transformer. The frequency is 50 Hz, has an iron loss of 1600 watts. The maximum efficiency occurs at 3/4 full load. Find the efficiency of the transformer at part number 1 full load at 0.8 power factor. The second part reads half load and the unit power factor. The third question reads the maximum efficiency. So what we are supposed to do under such situations is first of all to understand the concept that we are going to base the iron losses as our reference point, so that we would say at maximum efficiency, the copper losses should be equal to iron losses. That is what we know. At maximum efficiency, the copper losses must be equal to iron losses. Our reference point is the iron losses, where we say the iron losses are equal to the copper losses. But remember, what we have been given is that at maximum efficiency, the load level was 3/4. So we could say that copper losses, the solution, copper losses at 3/4 will be equal to 1600 watts. Remember, we use this squared. If you are dealing with copper losses, you have to square that fraction. But if you are dealing with power alone, you do not the output power. If you are dealing with the output power, you don't have to square the fraction. You take it directly as it is. So once we know this, we ask ourselves, what about at full load? Remember, we are talking about 3/4 load gives us this. What about when it is full load? Remember, here you can take 4/4. 4/4 is the same as 1. So I can either decide to write 4/4 or I can just take 1, which will be equal to what? So after you solve this, you will get 1 times 1600 divided by 3/4 squared. If you do your calculation, you will get it as 2845. 2845 watts. So meaning the copper losses at full load were 2845. But we know the copper losses at 3/4 were these. At 3/4 full load, the losses were 1600. But at full load, the losses are 2845 watts. That is the value. After you do this was just a preliminary. We can now go to Roman number 1, where we say, Roman number 1, remember what we asked in Roman number 1 is the full load and the power factor is 0.8. Full load and the power factor is that. Remember, what we have been given here is the power output. We have been given power output. Power out is given as 120 kVA. But remember, for purposes of calculation, you need to convert kVA into kilowatts. And we use this formula that now our P out in kilowatts will be equal to 120 times 0.8. Remember, from the power triangle, we know the real power, which is measured in kilowatts, is on the base of the triangle. So you need to use the cosine, because you know, if this is your triangle, then we have been given 120 kVA as that one, and we have been given this angle, of course, which represents the power factor. Then for you to get the kilowatts here, you'll have to take this one multiplied by the cosine of this angle. The cosine of this angle is what has been given as 0.8. So I'm saying that for you to get the kilowatts is the same as 120 times the power factor. And that is why we have multiplied on this side. So this one will give you, by calculation, that one should give you around 96 kilowatts. So the total output of that transformer is 96 kilowatts. After we have gotten that, we now want to look at the total losses of that machine. Remember, this is the output power, but we need to get the input power. So we need to get the total losses. We add the output for us to get the input. So total losses will be equal to copper loss plus iron loss. Remember now, total losses will be equal to our copper loss. Our copper loss is what we have determined here. Remember, we are looking at full load. The full load copper loss is 2845. 2845, that is 2,845. You sum the iron losses. The iron losses were 1,600, 1,600. Once you sum this, once you sum up the two, you should be able to get 4445. You get 4,400 and 45 watts as the total losses. Once you get that, we can now get the power input. Power input is equal to power out, is given by power output. Power out plus total losses. Plus the total losses. This gives us the power input. The power output was 96 kilowatts. 96 kilowatts is the same as 9,600 watts plus 4445 watts. That is 4,445. If you sum up the two, it should give you 100,000. To give you 100,000, remember this 4 multiplied to this gives you 100,445 watts. Now that is your power input. We are now moving into an area where we want to get the efficiency. Remember, we are just doing part 1. So the efficiency, which is denoted by this, is given by P out all over P in multiplied by 100%. This one should give you the power in. The power output is the power output was 96 from this point. Remember, this was our power output, which is 96,000 divided by the power input is 100,445. Then you multiply by 100. If you multiply by 100, you will get 95.57. 95.57%. So that one gives you now the efficiency of the transformer with regards to the first question. We're now moving to the second part of the question. Which we shall now move on to. Remember, the second part of the question requires us to get half load and unit power factor. The half load and unit power factor. So when we are solving this, the first step will be we need to get the copper losses at a half load. So part 2, we are working with the half load. So when we are dealing with the half load, we need to get copper losses at half load. Copper losses at half load will be equal to you will take a half squared multiplied by the full load losses. The full load losses were 2,845. Those are the full load losses. Once you do that, you will be able to get 710. You will get 710 watts. So 710 watts is the copper losses at a half load. Then of course we know the iron losses. The iron losses also come into play. The iron losses, we already know them, which is 1600 watts. We can now determine the power output. Power output at a half load. Power output at a half load is given by, remember the point is a half load and the unit power factor. In this case, we have to determine first of all the power output. The power output at unit power factor will be given by, we had 1200. We had 120 multiplied by 1, which gives us 120 kilowatts. Remember, this was kVA. We have converted it by multiplying by the power factor. You get 120. After you get that, then now we can be able to get power output at a half load. Will be given by a half multiplied by 120. Remember I said if you are looking for the copper losses, you need to square the fraction. But if you are getting the power output, you just take the fraction without squaring it. So this one gives us 60 watts. So this is the power output. After you have your power output now, we can move on and get the power input. Power input is given by P out plus P losses. So the power output is 60. Sorry, this was kilowatts. That is 60,000 watts plus the losses. The losses are 710 plus this one. So in fact we can add them here. Total losses will be equal to 1600 plus 710, which gives us 2310. So those are the total losses, and that is what we are going to add here, 2310. So if you add 2310 to that particular value, you will get 62,310 watts. So that is the total power input to the system at a half load. And if you want to determine the efficiency, the efficiency will be equal to P out divided by P in multiplied by 100. Once you do that, this is the same as our power output is 60,000 divided by 62,310 multiplied by 100. So if you do that calculation, this is 62,000, this is 60, it should be able to give you 96.29% as the value that you'll get for that particular question. Let us look at the last part, which is the maximum efficiency. We are now looking at the maximum efficiency. At maximum efficiency, we say, that is Roman number 3, maximum efficiency occurs at 3/4 full load. So we need to determine the parameters for 3/4 full load for us to be able to get the efficiency at 3/4 at the maximum efficiency. The first thing we know is the iron losses. Iron losses are given by 1600 watts, 1600 watts. But we have mentioned that at maximum efficiency, the copper losses, so maximum efficiency occurs at 3/4 full load, and copper losses is equal to iron losses. That is a statement which we can add there so that it's clear as I bring on board this. So the iron losses are 1600. Then it goes without saying that the copper losses will also be 1600 watts. Meaning total losses at that particular point will be equal to 1600 plus 1600, which gives us 3200 watts. So the total losses is 3200. And remember, we are working with a unit power factor, the maximum efficiency at a unit power factor. That means that our output power will be given by 3/4 multiplied by 120 multiplied by 1. Remember now these kilowatts, I'm taking 120 multiplied by 1 because I want to convert this 120 kVA to kilowatts. Remember, this is in kVA and we are supposed to work with kilowatts. So if you divide that, 3/4 of 120 should be able to give you 90, 90 kilowatts. So that is the output power. We need now to determine the input power. The power input. Power input is given by P out plus P losses. Remember, our P out is 90,000 plus our P losses. The losses are 200. So if you sum up the two, you will get 93,200 watts. That is the total power input. So we can now move a bit faster and get the efficiency. We know efficiency is equal to P out all over P in multiplied by 100%. This should give us the power output is 90,000 divided by 93,200 multiplied by 100%. Remember, if you do your calculation, it should give you 96,057. 96.57%. So the efficiency at full load is 96.57. So we will stop there.